All right, here we are to part 2 of section 10.4. This will be the last lesson in chapter 10. We're going to talk about arc length in polar coordinates. And here we have our cardioid that we've been using for quite a bit of this here. And here's the formula for how to find the arc length. We take r squared, so that would be that squared, times the derivative of that squared, and then we take the square root of that. Now, we're going to learn a new rule that we're going to use today. I'm not going to derive it on this particular video. If there becomes a demand for it, I can always do that. But we're going to use this. That is going to equal the integral from a to b of the absolute value sine of theta over 2 plus cosine of theta over 2 d theta. So we're going to use that at one point, but there's quite a bit of work before we get there. So I want to start by digging this part under the radical out. So I'm going to start with r squared. We'll do as much algebra outside the radical and everything that we can. So when I square that, that gives me 1 plus 2 sine theta plus sine squared theta. And the derivative of r with respect to theta is going to be cosine theta, which means dr d theta squared is just cosine squared. And putting all this together, so r squared plus dr d theta squared is going to be 1 plus 2 sine theta plus sine squared theta plus cosine squared theta. And we can see that this, of course, just becomes 1. And 1 plus 1 is 2. And I can even factor the 2 out. And you can see where I'm going with this. So when I take the square root of the whole thing, I'm going to get root 2 outside, and then the square root of 1 plus sine theta, which brings us to our arc length. Now, I'm going to do some fancy footwork here. I'm going to notice with the graph that the length of this arc to there is the same as the length from there to there. So I'm actually going to integrate from negative pi over 2 to pi over 2 and double it of root 2 times the square root of 1 plus sine of theta d theta. All right. Now I'm going to use my transformation up here. Now here's the good news. Negative pi over 2 to pi over 2, the absolute value becomes unnecessary. So 2 root 2. And we end up with sine of theta over 2 plus cosine theta over 2. Again, I don't need to put the absolute value because from negative pi over 2 to pi over 2, even sine is positive there, and cosine is definitely positive. So good news, sine is an even function, is an odd function, pardon me, which means that goes to 0, and because this is an even, I end up with, pulling out all the tricks today, we're going to end up with 2 root 2 times 2, the integral from 0 to pi over 2 of the cosine of theta over 2 d theta. All right, that extra 2 comes from going from 0 to pi over 2 and doubling it, because that's an even function. A lot of mileage out of that. Now, when I integrate this, once again, I'm going to get an extra 2 there. So this is 4 root 2 times 2 times sine of theta over 2 from 0 to pi over 2. And when I plug in the 0 there, that goes to 0. So I'm only going to focus on the pi over 2 here. So when I plug in theta here, it ends up being pi over 4. So we end up with 8 root 2. And sine of pi over 4 is root 2 over 2. And root 2 times root 2 is 2, over 2 is 1. The whole thing just ends up being 8. We used a lot of little tricks on that one. You may want to go back through the video and double check everything. Let's try another one that's not so full of tricks. All right. So we are going to start with r squared. Let's use some color here. So r squared is going to be 4 cosine squared theta dr d theta is going to be negative 2 sine theta, and dr d theta squared is positive 4, right? You square negative, you get positive 4 sine squared theta. So let's add those together, and we can do the square root. It's all good. So 4 cosine squared theta plus 4 sine squared theta. I can factor the 4 out, just becomes a 2 on the outside. And as we all know, this whole thing turns into a giant 1. Very nicely, all of that just becomes 2. We end up with the integral from, this is our arc length, from 0 to pi, that's what they gave us here, of 2 d theta. So 2 theta from 0 to pi is just 2 pi. Not too crazy. So we are going to find the length of r equals theta squared from 0 to 2 pi. So let's find r squared. So r squared, in fact, I'll do kind of what I did up here. R squared is theta to the 4th. And dr d theta is going to be 2 theta. And dr d theta squared is 4 theta squared. So the square root of adding those up is going to be theta to the 4th plus 4 theta to the 4th squared, pardon me, squared. And we can see theta is going to be positive, so I can actually factor out a theta squared, and then square root just gives me theta, square root of theta squared plus 4. And that becomes my integral. So the length is going to be the integral from 0 to 2 pi of theta square root theta squared plus 4 d theta. Now I'm going to do a substitution. I'm going to let u be theta squared plus 4. D theta is 2 theta d theta. We can see our du there. We're going to get an extra 1/2. Now our boundaries. I'm going to leave them in terms of just a generic a and b, because these are now u values. And I'm going to go ahead and integrate what we have. And I'm going to convert this back. So this will be 1/3 u, which is theta squared plus 4 from 0 to 2 pi. Oop, I forgot the 3/2. 3/2. All right, so let's see what we get. When we plug in 2 pi there, we're going to get 1/3. That's going to be 4 pi squared plus 4 to the 3/2 power minus 4 to the 3/2 power. And the 4 becomes, to the 3/2 power, becomes an 8. So this becomes 4/3. Oh, no, it doesn't. It becomes 1/3 times 4 pi squared plus 4 to the 3/2 minus 8. And I'm just going to stop there. And that is our final answer for that one. All right. We're going to go back to finding areas, but we're only going to set up the integral because these get quite tricky, actually. So what's going to happen is I need to find these two functions are, or this one function, pardon me, for this one here is r equals 2 plus 4 cosine theta. And the area of interest is actually this little tiny area here. And what I'm going to have to do is figure out the boundaries. Now, these boundaries get a little tricky. So what I'm going to do is I'm going to set the whole thing equal to 0. Which means cosine of theta is -1/2. Now, when is cosine -1/2? Cosine is negative in quadrants 2 and 3. So theta is going to go from 2 pi over 3 to 4 pi over 3. So here are the boundaries. And the integral ends up being, so the area of interest is going to be 1/2 the integral from 2 pi over 3 to 4 pi over 3 of r squared. So that's 2 plus cosine theta squared d theta. And I'm just going to stop there because they just want to set up. And some of these other ones are going to get even more weird as we move on. All right. So once again, for this one, here we have r equals 3 plus 2 sine theta. Here we have r equals 2. And I need to know what this angle is. That's looking like a negative angle to me. And what we're going to do is use a little symmetry and go from whatever that angle is to pi over 3. So I'm going to set these two functions equal to one another. So this means 3 plus 2 sine theta equals 2, which means 2 sine theta equals -1, sine theta equals -1/2. So this is going to be theta equals -pi over 6, it looks like to me. So our boundary is going to be, or our overall area is going to be 2 times, because I'm going to just go to pi over 2 here, 1/2 the integral from negative pi over 6 to pi over 2 now. So I don't need to know this one here. So I'm just going from here to here of the bigger function squared minus the smaller function squared. So 2 squared is just 4. All d theta. That is wild. For our next one, I don't have the functions here. So this function right here is r equals 3 sine theta. Sorry, I didn't type it. Actually, it just got erased accidentally. And this inner one is r equals 1 plus sine theta. So here are our 2 new functions. All right. Now, I want to acknowledge that we're looking at 2 very different areas. For this first part, just the red, theta is going to go from negative pi over 2 to 0. And that is just the one function. And that function is the 1 plus sine theta. So the first area, I will write out in red to make it clear. So the first area is going to be 1/2 the integral from negative pi over 2 to 0 of just this function of 1 plus sine theta squared d theta. That is just the red. Now for the green, which is the rest of the area that I'm interested in, that is going to be the difference of 2 of them. That is going to be from 0. And I'm on scratch paper here. I'm going to quickly see where they intersect. So 3 sine theta equals 1 plus sine theta. One half, that's when theta is pi over 6. So our new boundaries for the green is going to be 0 to pi over 6. Of function 1 plus sine theta squared minus 4 sine squared theta. That's all d theta. So we are going to get the overall area is going to be a sub 1, I meant black there, plus a sub 2. And so you would have to deal with each of those integrals either separately. You could try to mash them together to one big integral, but that's not necessary. Ooh, that's a lot of work. All right, this last one, again, we're just doing setup. I want to point out that there is a break right there. So for the first, so from 0 to whatever that angle is, we're only dealing with this curve right here. So it's just sine of theta. And then for after that angle, do you see we're only dealing with this curve? But what I'm going to do is notice that it is symmetric. So if I can find just this area, I can double that and end up with what I need. So what I'll need to do is set these two functions equal to one another. So sine theta equals cosine theta. Divide both sides by cosine, you get sine over cosine, which is tangent theta, equals 1. So theta, in this case, is pi over 4. So my overall area of interest, which is overall the whole thing, but I'm only going to integrate that and then double it. So here we go. The area is 2 times 1/2 the integral from 0 to pi over 4 of just the one function. So this is going to be sine squared theta. There is just the setup. So the integrals aren't too bad, but really having to kind of twist your brain a little bit to figure out what it is that you need to do can be a little tricky. Hope that helped.